Hello everyone, welcome to the experiment, Nucleophilic Substitution Reaction, Rates of Reactivities. We are going to look at SN2 and SN1 reactions for a list of 7 substrates. So for nucleophilic substitution reactions, we are always going to have a nucleophile come in and attack either a partially positive carbon or a carbocation intermediate. For SN2 reactions, we are going to do a backside attack and kick off the leaving group from a carbon which already has a partial positive charge on it. For SN1 reactions, the leaving group leaves, and then we attack the carbocation intermediate. In this experiment, we're going to use these 7 different alkyl halide substrates and put them under conditions. So for the first part of the experiment, we're going to put them under conditions for an SN2 reaction. For the second part of the experiment, we're going to put them under conditions for an SN1 reaction. For the different substrates, we have a variety of them. So this right here is a primary substrate, 1-chlorobutane. We actually have 4 primary substrates. So 1-chlorobutane, 1-chloro-2-methylpropane right here, 1-bromobutane, and benzyl chloride. We'll talk a little bit more about the expected rates for these compounds. But first, let's look at putting each of these compounds in a test tube, adding the different reagent and its appropriate solvent. So for the SN2 reactions, that's what we're going to start with. We're going to put 5 drops of these compounds in a test tube, and then we are going to add the reagent sodium iodide in the solvent acetone to see if we can get these to undergo an SN2 reaction. So here we have the test tubes already set up. We've got all of the test tubes labeled for what compound is going to go in each of them. We're going to add those compounds to the test tube with a dropper, adding 5 drops to each, and then we are going to add the solvent nucleophile combination shortly after that. So you can see each of those compounds in the background. Those are all liquid at room temperature, and we're adding 5 drops of each of those compounds to each test tube. And now we have sodium iodide dissolved in acetone, and we are going to be adding that to each individual test tube. There's actually a pump on top of it that you can't see that's set to 1 milliliter, which in the table of reagents that we'll look at later is equivalent to 1,000 microliters, and that is exactly how much we're adding to each of these test tubes from the pump on that solvent container. This is a close-up view of a reagent bottle dispenser. In this case, we have sulfuric acid, and we have a 10 milliliter reagent dispenser attached to the top of it. With all things in lab, we want to make sure that when we use this or any other chemical, we're underneath the fume hood. This has a protective cap on it, so that have to be removed before we actually run the dispenser. And right now, that dispenser is set at 5 milliliters. Before you use the dispenser, you want to put your flask or whatever you're dispensing into underneath it, because oftentimes when you lift up that pump, it's possible that a drop of liquid could fall out, just as did in that case. Right now, we've lifted it up. So when we pump that down, we are dispensing out 5 milliliters of solvent into our beaker. So we're going to utilize this approach. We're adding these in 10-second intervals, and if you look at these test tubes, it looks like 2 of them are already starting to turn cloudy. The 1-bromobutane and the benzyl chloride are both already starting to turn cloudy, and it looks like the 1-bromobutane is more cloudy than the benzyl chloride at this point. Looking at a close-up view again, it looks like our 1-bromobutane was definitely the fastest to react. It looks like that went almost instantaneously, but let's say for the having some substantial precipitate in solution, we'll say that was about 10 seconds after adding our strong nucleophile, and our benzyl chloride also. So we just clipped that out. It looks like not a lot happened. So that was essentially 8 minutes of the reaction. With the benzyl chloride, though, that definitely was second place. We had quite a bit of precipitate accumulate after about 5 minutes or so, and now we're just before the 10-minute mark. But we should note that 2-bromobutane had some precipitate in it. I mean, it was very faintly clouded, so I wouldn't necessarily call that the end time yet, especially when we compare that to our 1-bromobutane and benzyl chloride. So we'll put all those in the hot water bath. Keep an eye on it while it's in there, and then check it also as we go. Looking at our final products here, it looks like our 2-bromobutane, which did have some cloudiness in it, ended up with quite a bit of precipitate. So we, again, remember we didn't have our 1-bromobutane or benzyl chloride in the hot water bath. Those already went. We had plenty of precipitate in to call that an end time. And again, for 1-bromobutane, we were about 10 seconds, benzyl chloride about 60 seconds. Our 2-bromobutane was just slightly cloudy before we put it in. Quite a bit of precipitate formed in that, though. So our 2-bromobutane was definitely our third place reagent, so that reacted the third fastest out of our set of 7. Looking at what we saw, we'll say that that went at about 15 minutes for an amount of precipitate equivalent to what our 1-bromobutane and benzyl chloride had. And then it looks like our 1-chlorobutane was the last to go of things that we can clearly see precipitate, and that was essentially still not enough to necessarily say. So I would say 20 minutes for that got us pretty close to where these were when we called those an end time. So again, we'll say that the 1-chlorobutane formed precipitate after 20 minutes on the hot bath. For the remaining reagents, our 2-chlorobutane did not go, or 1-chloro-2-methylpropane did not go, which is surprising because that had a primary substrate. And then our tert-butyl chloride, or our 2-methyl 2-chloropropane, did not go either. All right, let's take a break on this video for a second and think about what happened for our SN2 reaction. So first, actually, let's go for this. So looking at our total time, we said 1-bromobutane was about 10 seconds. We said our benzyl chloride, we had plenty of precipitate at about 60 seconds. And for our 2-bromobutane, we accumulated quite a bit of precipitate after about 15 minutes. And for our 1-chlorobutane, that was some precipitate at about 20 minutes. So I'm not going to type in all these observations, but I'm just going to think out loud and type this one. So for 1-chlorobutane, there was no precipitate after 10 minutes at room temperature. Within the hot water bath, was seen at 15 minutes, and then slightly more precipitate was seen at 20 minutes. So that cloudiness in solution, just let me clarify, that cloudiness in solution is precipitate suspended in solution. So in this case, we're seeing sodium chloride suspended in solution. For our 2-bromobutane, let's just look at that too, so we can just talk about what we should say in here in direct comparison. First of all, for the table, definitely name these compounds. So again, for this is 2-bromobutane. So we've got a small amount of cloudiness, which is the same as precipitate, was seen at, which is precipitate suspended in solution, was seen at about the 8-minute mark. And then enough precipitate was seen at, so enough precipitate to settle to the bottom was seen at about 15 minutes. So with that, when you, within that explanation, you essentially want to explain that this went faster than that based on the visual evidence for the precipitate that was seen. And you want to basically continue that order just to make it clear that your observations are in sync with the time that you're calling it and the order that you're ranking these compounds. And hopefully we agree that this would be the expected rank. We'll talk about that order of reactivity and why this 1-chloro-2-methyl-propane is expected to be faster than our 2-chlorobutane compound. So again, don't forget to fill in the rest of these places. So name the compounds that weren't named, give the time for this, and give the observations for all of them. So going back to here, looking at our main reaction, we had a substrate with a leaving group on it for all of them. We also had sodium iodide as our nucleophile for all of them, and we used the solvent acetone for all of these reactions. So our sodium iodide was already suspended in acetone. We added a milliliter of that solution to our 5 drops of substrate. Our final product is our leaving group, whichever that was, so chlorine or bromine, was swapped out for an iodine, and we had precipitate, sodium chloride or sodium bromide form in solution. Looking at the mechanism for this reaction, if we draw that on here, so we have our nucleophile, our iodide anion. Now this isn't necessarily depicted as an iodide anion separated in solution, and that's okay. You can draw the mechanism where you have iodide as a anion standing alone, or you can draw it as the salt that it is. And we're doing a backside attack where our iodide comes in, attacks the carbon, and kicks off the leaving group. And that actually already gets us to our final product. So there's only 2 arrows in this mechanism. So this isn't super clear to see, so let's look at one of the faster reactions and look at why that reaction happened so fast. So we'll go ahead and draw the second place one. On your for your lab report, you need to draw the fastest. So you would need to draw 1-bromobutane as your example mechanism. I'm going to draw the benzyl chloride here as this example mechanism. So if we have sodium iodide, so I'm just going to order this a little bit different just to show that it doesn't really matter as long as you're above or below the arrow. This essentially represents the same thing as, so my reaction here, the way this is laid out, is pretty much the same as here, except I'm just more specific for what that specific R group is, what that carbon chain is attached to my leaving group. So we have our nucleophile, our sodium iodide. We're going to do a backside attack on that. Attack that carbon there, kick off our chlorine, and then our product. So the major product of this reaction is now going to be that. And I didn't show the specific stereocenter on this carbon right here. I didn't show that this iodide came in from the opposite side because this actually is not a stereocenter. So even though in 3 dimensions this is definitely doing a backside attack, you don't need to be specific in showing that for this. I'll show one more example where I am more specific just to clarify. But this is the product of the reaction, and this is what we're actually seeing in the test tube now is our sodium is in solution and our leaving group is in solution. So that sodium chloride salt is actually what we're seeing in solution, so we can get a stop time for the reaction. Now for this, like I said, our 1-bromobutane was the fastest to react, so we essentially had a primary substrate So our carbon here that our leaving group is attached to was attached to only one carbon, so we had a primary substrate. There's very little steric hindrance there. So we've got two hydrogens attached to that carbon. We can do a backside attack where iodide comes in here and kicks off that leaving group. Very similar to this, except that this carbon chain is actually a little bit more bulky, which makes you think that this should have gone a little bit slower. But our leaving group, our bromine, is actually a better leaving group. So that's going to drop the energy level of the transition state a little bit more than even having the less bulky backbone here. So this reagent is faster. We've got a primary substrate, but it's got a better leaving group, which you can use that to then justify why this reaction was faster than this one. But then the question is, why wasn't this one a little bit faster? So that was actually 4th place from our ranking. It was actually 4th place where this was 2nd place. So when thinking about that, we need to think about the hybridization of these carbons and really what's around here, and then also free rotation. So on these carbons, we have sp3 hybridized carbons, and we have free rotation around all of these bonds. So that is rotating freely, that's rotating freely, causing a little bit more steric hindrance on the backside attack. And I really need to emphasize that it's really causing more steric hindrance on this backside attack, especially because this one was the one that was 4th place. So when discussing this ranking, talk about the free rotation on this alkyl chain here, which is inhibiting our nucleophilic attack coming in right there to kick off our leaving group. So essentially this area of bulk is inhibiting that backside attack. Even though this carbon-carbon bond right here has free rotation, for aromatic ring, we have all sp2 hybridized carbons in this ring. So even though that has free rotation, this aromatic ring here is locked as planar. So you could literally imagine this ring is like a flat piece of paper, which does have free rotation, but there's really only 1 degree out of the 360 that's going to cause significant hindrance of that backside attack. So that's why this actually is quite a bit faster, because there is actually less steric hindrance. And this is slower than the first because the leaving group, our chloride anion, is slightly less stable, slightly higher in energy than our bromide anion, which that was the leaving group on our fastest substrate to react. We skipped over 2-bromobutane, which was in 3rd place. We have a stable leaving group, so that bromine allows that reaction to be sped up even though we have more steric hindrance for that backside attack. So that makes that faster than even our 1-chlorobutane. So this was 4th, and then I said our 1-chloro-2-methylpropane was expected to be 5th. So this compound was expected to be 5th, even though we didn't see any precipitate. When you're giving your explanation, go ahead and justify the total order of all 7 substrates. This was expected to be 5th because looking at this carbon, we have a carbon attached to 1 carbon. This chlorine is this whole compound is a primary substrate. So our chlorine is attached to a carbon that only has 1 carbon attached to it. Now, looking at the backside attack here, there's actually slightly more steric hindrance to that backside attack because we have an additional methyl group on a carbon, 1 away from the carbon that our nucleophile is attacking. So drawing in all these hydrogens might make that a little bit more clear. Essentially, there's a little bit more bulk in this area here than there is in this area here because our extra methyl group is right next to the carbon that we are attacking. So then you can go ahead and finish your explanation for why your 6th place compound and 7th place compound are where they are. It really all boils down to 2 things, and that is stability of the leaving group and the steric hindrance related to that backside attack. So stability of the leaving group and sterics are really how you're going to justify this. Now, how you're not going to justify this is talking about anything related to carbocation stability. A carbocation never forms within our SN2 reaction. Within that backside attack, a carbocation intermediate never forms. So you would never want to talk about anything related to carbocation stability, including resonance. That should not be discussed at all, including things like a 1,2 hydride shift. That can never happen because we never formed the carbocation in the first place. Resonance can never happen because we never formed the carbocation intermediate in the first place. So definitely do not discuss these things when talking about the order of reactivity for your SN2 reactions. For the table of reagents, for the reagents that we added in the test tubes, so for 1-chlorobutane and all of our alkyl halides, we added 250 microliters, so each drop is about 50 microliters, so 250 microliters total. And then for our sodium iodide and acetone, we know that we used 1 milliliter of a 12% weight per volume solution. So for the table, in order to figure out how much of our products we can make, specifically 1-iodobutane, which is the organic product of this reaction, and sodium chloride in this case is important because that's visually the precipitate that we're seeing in the acetone solution. So we can assess the rate of reactivity and order of reactivity for each of these compounds. So for the table, we want to start by figuring out the number of grams and millimoles of 1-chlorobutane starting material that we have. So for the measurable amount of something, that's always the best starting point, we have 250 microliters. So 250 microliters of that 1-chlorobutane. We can use the density to convert that to grams, and then use the molecular weight to convert that to moles. So for the density, that's in units of grams per milliliter. So we need to go ahead and convert microliters to milliliters. There are 1,000 microliters per 1 milliliter. At this point, our microliters would cancel. We'd be left with milliliters. Now we can use this density to convert our milliliters into grams. So 0.89 grams per milliliter, 0.89 grams per milliliter. Now milliliters cancels, and we would be left with grams. So you can go ahead and put this on your calculator, say 250 divided by 1,000. Times 0.89, that'll get you the number of grams. I'm just going to keep going though so we can get to millimoles. Okay, so now that we're at grams, we can use the molecular weight of this equation, so 92.57 grams, and moles is on top, so this is in units of grams per mole. Moles on top, we have 1 mole on top. The table asks for millimoles, so we need to convert moles to millimoles, and there are 1,000 millimoles for every 1 mole. Alright, so now plugging this whole thing into your calculator and you'll end up with the number of millimoles of 1-chlorobutane. My guess is that's going to be higher, and that's going to be our not our limiting reagent. So my guess is our limiting reagent is going to be our sodium iodide and acetone. So let's look at that calculation. So in this case, we have a 1,000 microliter volume. So 1,000 microliters. If we convert that to milliliters, then we can use this weight per volume to convert our milliliters into grams. So I'm going to convert this to milliliters, same as before, 1,000 microliters per milliliter. Now that we're at milliliters, we can use this weight per volume. So this percent is grams per 100 milliliter. If we have 12%, we have 12 grams per 100 milliliters. When we solve for that, that'll get us 2 grams. I'm going to keep going though and just go ahead and get to our millimoles. So for the millimoles, we need to use the molecular weight to convert grams to moles. So 149.89 grams, and that is 1 mole on top. So if we solve this, we'd get to moles. We want to get to millimoles. 1 mole per 1,000 millimoles. And I'm putting millimoles on top. Moles needs to be on the bottom, so that cancels with that. Millimoles is on top. Hopefully when you calculate this, like I said, this number is going to be more. This is going to be about 0.80. And like I said, if this is less, which I think that it will be, then that means that sodium iodide and acetone is our limiting reagent. So 0.80 millimoles of sodium iodide and acetone, this is going to run out first. So this determines how much of our products we can make. Specifically, the sodium is going to run out first, making our sodium chloride, and the iodide is going to run out first, making our iodobutane. These are at a 1 to 1 to 1 mole ratio, meaning that for every 0.8 millimoles of starting material, sodium iodide, we have, that is how many millimoles of each of these we can make. So now that you hear that you have millimoles and your molecular weight, you can convert these to moles and then use these molecular weights to find the number of grams of each of these.